So good afternoon, everyone. Good afternoon. Am I audible?
Yes, ma'am.
Yes. Okay. Good. Okay. So yeah, just before we continue with linear programs, just one point I just wanted to clarify about these negative definite matrices. So this is something that Rajneesh brought up. So I'd like to thank him. And so this point about matrix being negative definite, it means that all for all x in Rn you have x transpose Ax less than 0. So that's the thing we saw, and that boiled down to all eigenvalues of A being negative. Okay, and another way to say this is that if x transpose Ax is less than 0, you have that if you take minus A, you're going to have x transpose minus Ax will be greater than 0 for all x in Rn. Okay, so whatever, if you want to test if a matrix is negative definite, you can use the Sylvester's criterion on minus A. Okay, so yeah, I made a mistake when I was discussing the midterm answer sheets when I talked about this aspect. So the Sylvester's criterion, if a matrix is positive definite, what it means is that you take this entry that has to be greater than 0. Now you take the the second principal minor, so composed of these four
Ma'am,
entries. Yes.
ma'am, your screen isn't shared with us.
Oh, thanks for telling me. Yeah. Yeah. Okay. Yeah, thanks. I think now it should be visible, right?
Yes, ma'am.
Yeah. Good. Thanks. Yeah. So what I was saying is that when you want to test whether a matrix is negative definite, what you could do is use the criterion for positive definiteness on minus A. Okay. So that would mean that if this is the matrix minus A, let me just call it for any other, any positive definite matrix. Let's call this X. Okay, so if you want to check that X is positive definite, that would mean that you take all the principal minors and those have to have a value greater than 0. So those are all determinants basically. So the first value has to be greater than 0, the first element here. Now, if you take this submatrix composed of the first k entries, first k rows and first k columns. So in this case is the first two rows and the first two columns. This has to be greater than 0. Similarly, like that for every k you take. Okay, and finally the whole matrix. So determinant x also has to be greater than 0. So now when you say that minus a is positive definite, what this would mean is, again, yeah, each of these determinants of minus a should be greater than 0. So that would mean that this entry has to be less than 0. Okay. Now, if you take this determinant, so this is actually the, just if you take this as the, the value boils down to the principal minor of A. Okay, and with a minus 1 power 2 because you're taking off the minus sign from these two entries. So this will again have to be greater than 0. Now when it comes to third element, you're taking a minus 1 out from the first three rows. Okay, so that would mean minus 1 to the power 3 of the third principal minor of A3. So I'm just calling it this way. So this has to be greater than 0. So that would mean that, A3, the principal minor A3 has to be less than 0. So you'll have this sort of alternate kind of behavior. Okay. So thanks, Rajneesh, for pointing this out. Okay. So I just wanted to share this with the class. Okay. All right. So I think now let's get back to our discussion on linear programs. Okay. So we were looking at the simplex method again. And yeah, just to again remind you of it, so where we were focusing on optimal basic feasible solutions. Okay, and where I start off by identifying some basic feasible solution and you see if it's optimal. If it's not optimal, you identify a new basic vector and which has to enter and another basic vector to leave the system. So this way you're kind of moving to adjacent extreme points, okay, in the hope of going to an optimal. Okay, so we were looking at this step by step. So we started off with 3b, where we know that the basic vector to enter. At this point, that has been identified, and we saw how to decide on a vector to leave the system. Okay, so this is what we did yesterday. Okay, so I just wanted to, like in this example that I took yesterday, I showed you how to choose the one to leave the system, but I just wanted to, just write the revised tableau once with you guys. So just for the sake of completeness. Okay, so here what we decided was, we knew that this first column was going to enter the basis, and we had to choose one of these three. And then we took this ratio 5 by 1, 3 by 2, and 1 over minus 1. And the smallest was this value corresponding to this row. Okay, so each of these rows also corresponds to a basic variable. I mean, each column, of course, corresponds to a variable in the system, but the rows now correspond to a basic variable. So the first row corresponds to x4, the second row corresponds to x5, and the third row corresponds to x6, because you get the values of the basic variables by looking at each of these rows. Okay, so now this one was going to enter, the first column was going to enter, so which meant that in the new basic feasible solution, x1 would be a part. So now you had to decide between x4, x5, x6, and based on these ratios, we decided that x5 was going to leave the system. Okay, because of these three ratios, 5, 3 by 2, and minus 1, the lowest positive value, or the lowest non-negative value was 3 by 2. Okay, so this column was, going to be like what you call the pivot. And in fact, this one was going to leave. So this column was going to leave the system because x5 leaves the system. Okay, so then what it means is that the first column has to be made 0, 1, 0. Okay, so now this, in the revised tableau, you want the first column to start like this, 0, 1, 0. Okay, so now to do that, what you will do is row operations. So you will divide the second row by what? How would you make this 0, 1, 0? Can you tell me the row operations for that? Can someone tell me the row operations?
Ma'am, we'll divide the second row by 2.
By 2, right. So that will give you what? Can you tell me the entries?
Ma'am, it would be 1 minus 3 by 2, and I don't know the rest.
Okay, so then this would be 1 by 2.
1 by 2 and 0 and 1 by 2 and 0.
Okay,
And
so
3 by 2.
Right. So 1 by 2, 0, 1 by 2, 0, and 3 by 2. Okay, so this is the second row. So this is all the modified values of B. Okay, and the first row, you want this part to become 0. So what you will do is you will subtract R1 minus half R2, right? So how you got this is first you did R2 by 2, okay, and R1 minus R2 by 2, okay. So that's going to give 0 here. Can you tell me the other entries? Can somebody tell?
Ma'am, it would be 5 by 2.
Okay, 5 by 2.
Then minus 2. I'm not sure.
Minus 1?
Minus 3 by 2.
Exactly, minus 3 by 2. And
1.
This is 1 itself, right?
Minus half and 0.
Minus half and 0, right? And the last entry here would be
7 by 2.
5 minus 3 by 2, right? Yeah, correct. 7 by 2. Okay, that is this first row is taken care of. So this would still correspond to x4. Okay, now this corresponds to x1. Okay, so let's write the last row as well. So in the last row, we had a minus 1 here, and that had to become a 0. Okay, so the way you would do this is you would take the last row and add half times the second row, right? So R1 becomes this, and R3 becomes R3 plus R2 by 2, right? So can somebody tell me what is going to be? So the first one is going to be 0. And what's the second one?
It would be half.
Half, right? Next one,
Then minus half.
minus half,
Then 0.
0,
Then half. And then 1.
half, 1. And this last one would be
5 by 2.
5 by 2. Okay, so this is going to be the new tableau. Okay, and so the first column, so these are the basic vectors now. Okay, so you can see that it's all the identity elements are not together. They can be spread out in the tableau. Okay, so the first row corresponds to x4. So this is the basic variable it corresponds to. The second row corresponds to x1. So x4 is 7 by 2 as per this. X1 is 3 by 2. Okay, and the last one corresponds to which basic variable does it correspond to? Can somebody tell me? Guys, let me ask somebody. Bhavna, can you tell me what it corresponds to?
Ma'am, can you repeat?
So I'm just trying to see what are the variables that each of these rows correspond to. Like we were saying that each of these rows also corresponds to a basic variable, right? Because there are m rows and exactly there are m basic variables. So from the first row, you can get the value of x4, right? X4 is 7 by 2 because
yes, ma'am.
right. So I'm just asking, what is the last row? Which one does it correspond to?
X6.
X6, right? Okay, so these are the new set of basic variables. So x6 is 5 by 2 and all others are 0, right? So all others are non-basic. So x2, x3 and x5 are 0 and they are non-basic. Okay. Right, so these become the new basic variables. Okay, so I just wanted to, complete this step here. Okay, so and you can see that, all these values, as we rightly wanted, that these are all greater than or equal to 0, so they're feasible. Okay, so just try out what happens if the second column has to enter. So now we took that the first column was entering, so x1 was entering. So suppose instead of x1, you wanted x2 to enter the basis, what's going to happen? What's the revised tableau going to look at? So you can work this out yourselves. Okay, so we saw this alternate view also, which explains why these kind of operations work. Okay, so now I just wanted to move on to the case where you want to decide. So till this point, I told you that the new basis element that enters is given to you. Okay, so now how would you choose this basis element? Okay, how do you choose the next element? So this is the stage where, of course, we need to make use of the objective, right? So in the previous 3B step, we didn't make use of the objective at all. So while choosing the new element which has to enter, you have to look at the objective. Okay, so let me just go into the alternate view first because maybe this would be a lot of algebra. So the other view, I felt like yesterday, maybe that is more easier to follow first. So in terms of the current basis, you have this A1 to AM. Okay, and there is all this AQ and everything is there. I mean, there are several such elements here, and now you want to decide on what is the AP which has to enter. Okay, so if you propose to include AP in the basis, okay, then what? Okay, like just ignore this part, the remove AQ part. So what is going to happen is, you have the current solution B, which is written as the linear combination of these AMs, and the weights of, with which you combine these A1 to AMs, that's given by X1 to XM. And the original objective here is C1X1 plus so on plus CMXM. Okay, so this is the objective with respect to this basic feasible solution. Of course, you have a Cm plus 1, Xm plus 1, and so on up to Cn Xn. Now all these are 0, so this part just becomes 0. Okay, so in effectively these are the ones which decide. Okay, and now if you look at this AP, which is the new element that you want to include, and you have to decide this. So every element, every other non-basic vector that you have can be written as a linear combination of A1 to AM, because this is a basis, right? And in particular, you can, because here we have the identity. Okay, so because the in the simplex tableau, what we took as the basis was the identity. So every other column you take, you write it as, you can write it as, if you take the m plus 1th column, you can write it as y1 m plus 1 times the first column plus y2 m plus 1 times the second column, and so on up to y m plus 1 times the last column. I mean, the last column of this identity. Okay, so effectively what happens is, you can write it in this way. So the pth column, if you take, you can write it as this: y1p times a1 plus so on up to ynp times an. Okay, so now if you are going to include ap into the basis, now the objective that's going to happen, that's going to result from the new basic feasible solution, what you're going to do is you're going to include P and you're going to remove some Q, right? So in the process, you're going to, multiply this with epsilon, okay? And, like add it to this part, right? So from both these, from this equation and this equation, what you're going to get is the solution is x1 minus epsilon times y. Okay, x minus epsilon times sum of the y's. So the corresponding thing for x1, the first basic variable, is going to be x1 minus epsilon times y1p. Okay, this one. So it's just like saying, AP. So epsilon AP is, okay, so minus epsilon y1p times a1 minus all these minus epsilon ymp times am is 0. Okay, so it's you can just add these two. Okay, so add this equation and this, this one. Okay, so that's just going to give you x1 minus epsilon y1p, okay, times a1, right? So maybe just an intermediate step. We saw this yesterday, so but anyway, let's just write it again. So x1 minus epsilon y1p times a1 plus x2 minus epsilon y2p times a2 plus so on, plus xm minus epsilon ymp times am plus epsilon ap is going to be 0. Okay, so now, sorry, this is going to give you b, right? So this is b and this is 0. Okay, I'm just adding these two equations. So now if, this can be viewed as the new point, x1 minus epsilon y1p, x2 minus epsilon y2p, and so on. Okay, xm minus epsilon ynp, and additionally for ap, for xp, that you're going to have it as epsilon. The value was 0 originally, but now you're going to set it to some epsilon. Okay, so now for this kind of a solution, the objective when you take, that's going to give you C1 times this value, x1 minus epsilon y1p plus C2 times this, and so on. Okay, and for the pth variable, you're going to have the coefficient as Cp times epsilon. Okay, so now originally you only had C1, x1, Cm, xm, and up to Cm, xm. Okay, so let's just take that part out. So that is this first term that I've written here. So this is what was the objective of the original basis. And now if you are going to bring in Cp, the pth vector, you're going to additionally have some other terms here. Okay, so now each of them you can write like this is corresponding to the value of epsilon. So I'm just trying to group it based on the x's. So it's as if this epsilon is going to be substituted for xp in the new basic feasible solution. Okay, and if you look at the coefficients of this epsilon, that's going to be Cp here. Okay, and wherever this epsilon comes, you'll have C1 y1p, C2 y2p, and so on up to Cn, Ym, P. Okay, so that is this term. Okay, so there is going to be this extra term that's going to get added. Okay, and so now, this is going to take the value of xp. That's what we saw earlier. And suppose this coefficient here, if that is going to take a value less than 0, then what is going to happen is that this new solution that you get here is going to be better than the previous objective, right? The previous objective was just this, and here is a value, here is a solution, which is giving you a better objective. So our objective was to minimize C transpose X, okay? So here by doing this, we are getting a better solution, right? So then you can see, like, you can compute these this quantity here for every other non-basic column. Okay, so CP. So P is the one which corresponds to non-basic column. You compute this quantity, and you see which is the one which is the you see the ones which are less than 0. Okay, the negative ones, and the most negative one you take, because that is going to yield the maximum improvement in the objective. Okay, so is this idea clear? I will go over this with an example, but is this step clear to you, like why we are looking at it in this manner? You can type in the chat box, or if you have any questions, please ask. Okay, Manan, is it clear?
Yes, ma'am, the idea is clear, and I think after seeing the example, it would be better.
It will be better. Okay, so let us maybe just go over this example. Okay, so I'm just taking.
Is there a plus sign there? I think.
Which one?
Sigma equal to 1 to n Ci xi plus epsilon.
No. So that is coming here.
The plus epsilon or minus epsilon.
Oh, this one. Yeah, this has to be plus epsilon. You're right. Yes. Thanks, Rajneesh, for bringing this. Yeah, this has to be plus epsilon. Okay. So that's when this will improve. When this part becomes negative, this overall term becomes less than summation Cixi, right? Okay. So yeah. So let us just see this example here. Okay. So now I'm taking this one, minus 3x1 minus x2 minus 3x3, and these are the constraints. So I'm adding some slack variables x4, x5, x6, and this is the tableau that I'm starting with. Okay, so what I've written here is the costs corresponding to each of these variables. So for the first one, so this is in the objective. Okay, so the objective costs. Okay, and this corresponds to the first column. So you have a cost of minus 3. And for the second one, x2, you have a cost of minus 1. And for x3 is a cost of minus 3. And x4, x5, x6 are additional variables, the slack variables. So it's as if there is a 0 cost for them. Okay, so that's why these costs are 0. Okay, and now as usual, I've just written the tableau. So let's just come to this column, the 0, 0, 0 column a bit later. The rest of it, starting from the 2, 2, 1, 1, 1, 0, 0, 2. So this is the usual tableau that you saw. And then you have a 1, 2, 3, 0, 1, 0 corresponding to the second constraint, and so on. Okay. Now, as per this, I'm fixing this as my basis. This is the identity, and I'm taking x4, x5, x6 as my basis. Okay. So now, so that's what even each of these rows corresponds to x4, x5, x6, and they have a cost of 0. So this cost I've written here in this column. This corresponds to the cost of the basic variable. Okay. Okay. So now, and you have B is 2, 5, 6 as per this. Okay. So now I'm just going to call this quantity as ZP. Okay. The CIYIP. Okay, so now let's just see what to do here. Okay, so these were the costs. I mean, these are actually the cost of the basic variables. So that those double up as this CIs, I equals 1 to m. So remember, this corresponds to the basic variables, and here the basic variables are x4, x5, x6, and these values are 0, 0, 0. Okay. So now what you do when you compute this ZP, summation Ci YIP. So let's take the first column and let's compute this number. Okay. You have to do this for every column, every non-basic column you have to do this. So let's start with the first column. Okay, so these YIPs correspond to these columns, right? 2, 1, 2. So that is the first column, and that's exactly the value of these YIPs. So what you do is you just multiply these two. So 0 times 2 plus 0 times 1 plus 0 times 2. So that's going to give me 0. Okay, and the cost here, the CP. Okay, so that corresponds to the cost of the non-basic variable. So here in this case, the cost of x1. Okay, whichever column you're proposing to include as a basic variable. So the cost of that, so that's minus 3. Okay, so I've just rewritten this here, the same thing as this. And so that's going to give you minus 3. Okay, so now if I subtract out, so this term CP minus ZP or CJ minus ZJ here. So C1 minus Z1 here, it's just minus 3. Okay, so maybe let me just let us do this together so that it's easier to follow. Okay, so is this thing clear, like how we computed it for the first column?
Can you repeat it?
Yeah, you want me to repeat it? Yes. So we are basically computing this term, okay, for each of the columns P. Okay, so for each of the P, which is a non-basic variable, we are computing this. So remember the YIPs, it just corresponds to the entry in column P. Okay, so that's what we had in this basis, right? I mean, that was our notation. So Y1P, Y2P, and so on. So that's what you do here. Yeah, so these are the YIPs. Okay, so in order to compute this quantity, summation CI YIP, so CIs here correspond to the cost of the basic variables, and that is what is 0, 0, 0 here. Okay, so this quantity, just this summation CI YIP, which I'm noting as ZP, it's just 0 times 2 plus 0 times 1 plus 0 times 2. Okay, so that gives you a 0 value. Okay, and CP corresponds to the actual cost of this, including this basic variable. I mean, including this non-basic variable. At this point, it's a non-basic variable, so the cost of this one. So that is minus 3. So this difference between CJ minus ZJ is minus 3. Okay, so that is the one, that is exactly this term. Okay, and so this is negative, so it means it could lead to an improvement. Okay, if you include this, you're going to get a solution with a better objective. Okay, Rajneesh, was this step clear? This computation?
Yes, ma'am.
Yes. Okay. So let's just do this for the other columns. Let's do for these two columns as well and see what it gives. Okay. So what is going to be ZJ for this second column? Can somebody tell me?
Zero.
0. Yeah. Because why was it 0?
Coefficients are 0. Cost.
0. Cost is 0. So you just take 0 times 1, 0 times 2, and 0 times 2. So that gives 0. And right. And the CJ is what for this column?
Minus 1.
Minus 1. Yes. Good. So now this difference is going to be just minus 1, right? The difference between CJ and ZJ. So what about the third one?
ZJ is a 0 for all these.
All of the zeros, and CJ is again the same,
Minus
right?
3.
Minus 3. So this will be minus 3. Now again here also, so this is always going to be 0 because all the costs are 0. Okay, and if you look at CJ here, this is also going to be 0. And so this difference for the basic variables, you're always going to get this as 0. So sort of that's the best you could have done for these basic variables. So now if you look at this entry, Cj minus Zj, there are 3 values which are negative, right? So if you choose any of them, there will be an improvement in the objective because that's what this told you. Okay, so so we are very greedy in this in choosing the basic variables. We want maximum improvement at each time. So let's choose the most negative value. So you could choose either x1 or x3. So let's just say this is going to, so then we finalize that this is, I mean, you can choose, you can break ties arbitrarily. So this is the one which is going to uh, enter the basis. Okay, so now so we fix that x1 is going to enter. So after this, now you have to choose, you have to do the other step which we said. So x1 is going to enter, and at the moment the feasible solution that you have is x1, x4. I mean, the potential candidates are x1, x4, x5, x6. You're sure you want to include this. So one of these 3 has to leave. So then you apply the previous step. So you take this ratio. So here now the ratios will come into play. Okay, so this is going to give you, what is it going to give you? Can you tell me this?
1, 5, and 3.
1, 5, and 3. Okay, so now what's going to happen? The lowest value is this one. Okay, so that corresponds to this row. So what you're going to do is you're going to move x4 out of the system. Okay, so now you will again redo this tableau. You will make this column as 1, 0, 0. Okay, because this x4 is going to leave. So in place of 1, 0, 0, this column is coming in, and that should have 1, 0, 0. Okay, so this process is going to repeat till you reach a point where you do the step, the Cj minus Zj's, and you will see that, and you can't find any of them for which the value is like negative, okay, which is less than or equal less than 0. You're not going to find any such variables. So that means as per this step, all these value for all the non-basic variables, this is going to be greater than 0. Okay, so that means if however you go, you're going to get worse off. There's no way to become better, and so that means you have reached an optimum. Okay, so this is the way in which you test for when to stop. Okay, so yeah, so I hope this has been clear. Are there any questions up to this point?
Ma'am,
Yes, Viranj.
if the objective is to maximize that particular, then we will be choosing Cj minus Zij to be maximum, right? From
Yeah.
all the values.
Yes. So usually this the simplex method is devised assuming that the LP that you give is in standard form. So standard form is in a minimization form. So that's why everything is written with respect to the minimizing operations. Okay, but yeah, if you wanted to maximize, you would go the other way. Okay, so any other questions?
That epsilon is for just for the ratio we are calculating. What's the rule of that epsilon particular?
This epsilon, yeah. So this comes from the value of this xp, right? So once you decide to include xp, this is going to be the value of this the new variable. If you decide to include that, this is going to be epsilon. And so based on the our previous discussion, you will fix this epsilon to the extent possible. So that's why you try to see this is going to be fixed based on the one which gives an improvement. So now if you try to increase epsilon as much as possible, then you get the greatest improvement, right? So one thing is choosing the p for which this value is as low as possible, the Cp minus Zp, the lowest negative value. Okay, so that is what you choose. Now, once you have decided that also, in order to get the maximum improvement, you have to choose the epsilon as large as you can, right? But when you do so, the issue is that, you also want to be at a basic feasible solution. So as far as XP is, you are fine. You're going to have, if you make epsilon even larger and larger, it is going to be okay. But you also want to ensure that, the rest of the variables are feasible. Okay, so you also want to ensure that when you do this equation, right, this x1 minus epsilon y1 a1, so this whole thing equal to b, that is also satisfied. Okay, and you want to increase epsilon here, but at the same time, what is going to happen is some of the values are going to decrease. Some of the other variables, xq minus epsilon yqp. So this is what we were discussing yesterday. So some of them will decrease, right? So then you don't want them to become infeasible. So if the ones that are going to decrease, you don't want this xq minus epsilon yqp. Suppose it's going to decrease, you don't want it to go less than 0. Right? So that's how you fixed epsilon as the minimum value, this xq by yqp. That's why you chose this as a minimum value, so that all these entries are also greater than or equal to 0. Okay, does that make sense?
Yes, ma'am.
Yeah. So it's actually, there are like multiple steps which are entwined. So each of them, there is some effort involved in the process, the steps that are there. Okay, so so up to this point, it probably might have been hazy, like why we are doing so many things. I mean, but I hope with this, with these 2 steps completed, I hope you get the overall picture of this. So, are there any more questions on this?
Ma'am, the leftmost column which you wrote 0, 0, 0. So, so will that change if x1 comes and so what will
Yes.
happen to that column?
Yes, let's do that now, right? So maybe we'll do one more step, it will become clearer. So let's do this thing of, let's replace this with a new variable. So we said that x1 will enter and the smallest ratio was corresponding to x4. So this is going to leave the system. So let's write the new tableau, right? Now we know to do that. So the first one has to become 100. So this, let's write the costs later. From this tableau, from this part onwards, the first column has to give 100. Okay, so can you tell me, can you fill the tableau? Can you tell me the first row? If you want the first column to be 100, what's going to be the first row?
Point five, 0.5, 0.5, 0.5, 0, 0, 0.
Yeah, so I'll just write it as half, 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 then 0, 0, 0. Yeah, it's 2 zeros, right? Half, 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 0, 0. And here you had 1, right? 2 by 2 also. So this is going to be 1. So what I did is just R1 by 2. Okay, R1 becomes R1 by 2. Now the second row is going to be what? So you want this to be 0. So all the operations will be done with respect to this as the pivot. So what is the operation you need to do to get this as a 0?
R2 minus R1.
Yeah, so R2 minus this row, or if you were taking with respect to this, it would be R2 minus the original R1 by 2, right? Okay, so I'm just writing it this way, R2 minus R1 by 2. So this is the new R1. So can you fill this up for me? So this is 2, 1, 2. So this is 2 minus half, right?
3 by
Right.
2, 5 by 2.
3 by 2, 5 by 2. Okay. And
Minus half.
minus half. So that corresponds to this one. And this are 1 and 0, right?
Yes, ma'am.
Minus half, 1, 0. And this would be 5 minus half, right? So that would be what? 5 minus
4.
half times 2. So 4, right? Okay, so I'll just draw this line here to separate this. Okay, and now the last one is you want this entry to be 0. So that is going to be what? What operation does that? So with respect to this pivot,
R2 minus 2 R1.
so it's just R3 minus R1, right? Right? Because it's this and this. You always do the operations with respect to this as the pivot. Right? So R3 minus R1. So the new R3 is going to be the original R3 minus the original R1. So this give you 0. So what are the others? Can somebody tell me?
1 0 minus 1.
1 0 minus 1. 1 0 minus 1. Okay, this is 0 and this is going to be 1, right?
0 1 4.
And this is 4. Right. Okay, yeah. So now we have this tableau. Okay, and so let's just write the costs now. So this is a tableau, and so this corresponds to x1. So the cost here, cost of the basic variables. So that's what you write on this side. So that's going to be the cost of, this was x1. So x1 had a cost of minus 3. So this cost here would be minus 3. And this corresponds to x4. So this was x1, this was x5, right? x5, and this is x6. Okay, so x5's cost in the original objective was 0, and x6 is also 0. So this will become 0, 0. Okay, so now let's just again compute the zj's at this point. Okay, so can you tell me, so the non-basic variables are these. So let's just compute it for these 3 columns, the second, third, and the fourth columns. So can someone tell me the zj values? So what you do is you just multiply this times this times this, plus this times this. So
minus 3 by 2.
Yes, minus 3 by 2. And for the third column, for this column,
Same here. Minus 3 by 2.
same minus 3 by
Minus
2
3
and
by 2.
minus 3 by 2. Okay, and what about the basic variables? What happens?
Minus
So it is
3.
minus 3,
0 0.
0, 0. Okay, so so these are the zj's. So that is this value, and the cost. Let's write this. So the cost of so this is going to be the cost of these variables, whichever you're considering here itself. So the cost of x2. So that is what? Minus 1, right? So this is minus 1. And for x3, what's the cost? So it's minus 3, right? And x4, x5, x6 is 0, 0, 0. And x1's cost is what? Again, minus 3, right? From the objective. Okay. So now let's compute this CP minus CJ minus ZJ. So can you tell me the values?
Zero.
0,
1 by 2.
1 by 2.
Minus 1 by 2. Minus 3 by 2.
So
Minus 3 by 2.
so this is minus 3 plus 3 by 2. So minus 3 by 2.
Plus 3 by 2.
Yes.
0 0.
0, 0. Okay, so this is now the reduced, these values are actually referred to as the reduced costs. So it's the original cost minus some value. So these are the reduced costs. So at this point, what is going to happen is you identify that x2 is going to further improve your objective. Every other thing is it's greater than 0, right? So they won't lead to an improvement. This third one, so x3, if you include x3 as a basic variable, that's going to improve. So now you again repeat this process. You try to identify which one will leave the system. So let's just do this one more time, which one leaves the system. So let's just identify up to that, and you can complete the steps later. So now can you tell me which one is going to leave? So just 1 second. So before that, what I just wanted to clarify. So from this tableau, what we are going to get is x1 is 1, x5 is 4, and x6 is 4. Okay, so I just wanted to also mention that. So this is the new solution, and all other variables are 0. Okay. All right, so can you tell me the new ratios now? Which one is going to leave the system at this point? So this is the B's, the modified version of B's. Guys, can you tell me?
Ma'am, 2 8/5 and infinity.
2 8/5, and this is no different. So this is infinity. So anyway, you don't count this. So you take the lowest value. So that is again going to be this one, right? 8/5. Right? So that's the lowest value. Okay, so what you will do is now you're going to make x5 leave the system. And yeah, x3. So this is x3. Yeah, x3 is going to enter and x5 will leave. So you will modify the tableau accordingly. This will become 0 1 0. This third column will become 0 1 0. Okay, so I'll leave it as an exercise to complete the simplex procedure for this example. So I hope this is clear, right? The sequence of steps. Are there any questions on this?
Actually, steps are clear, but I have another doubt here.
Yes, tell me.
Ma'am, so what we did in previous step, there were 2, -3 and -3. We chose arbitrarily one and just optimized based on that. So we finally, after doing all these steps, we will get to an optimal. But
Yes.
what if we have chosen that other -3 and we would have gotten to other optimal, which would be much better than that?
So that can also happen. So maybe you could have chosen this as the next step, as x3 as the entering variable. Okay, and then you would have got a different trajectory. That is fine. But so one thing to remember is, however you do this, like in these choices, I mean, both these are actually equal. I mean, in terms of the improvement that you're going to get, both are going to give you the same improvement in one step. Okay, so you can keep doing this, follow the different trajectory, but ultimately the optimum that you're going to get is going to be the same. I mean, the same value you're going to get as the optimum. Now, if there are multiple basic feasible solutions which give the same optimum, that can happen. Okay, but so this doesn't guarantee like which BFS you're going to get. So you will get one of the BFS which give you the optimum solution. Okay, so yeah, that's actually a good exercise for you to try. What happens when you choose, if you choose x3 at this step? Okay, so actually one thing you can note here is that after choosing x1, in the next step, like now we found one more tableau. We chose x1, x5, x6, and actually now in the next step, what is going to happen is you're going to choose x3 to enter. So actually x1 and x3 are both going to be part of this basic feasible solution. Right, so something like that will happen if both are going to contribute well. If you start with x3, even that will, if there is an improvement in including x1, you're going to get that in some future step. Okay, but yeah, in general there can be multiple optimums, so you just guarantee that you will pick one of the optimum. You will reach one of the optimum. Okay, Rajneesh, is it clear?
So we will reach to the same optimum value. Yes,
the final objective that you're going to reach will be the same. So the reason is this is a convex program, and it's a particular case of linear objective and linear constraints. Okay, so
here when we were looking at it geometrically, so we were taking some lines and watching that feasible diagram, feasible region. So we are now what we are doing here, we are jumping from one vertex to other vertex here.
Yes.
So finally that diagram should be convex, a convex figure in any dimension. So do we have do we have proved it, or we'll prove it, or what will be then?
I'm not sure I got your question. Can you say that again?
Ma'am, actually, if we are reaching to the same optima, then it is because that figure in n dimension is a convex figure.
Yes.
So where have we proved that it is a convex in other way? that should be a convex to reach the same optima. So is it always the case that that figure is convex?
Yeah. So that is coming because of the structure of the problem, right? Because it's a linear program. So what you have is something like this, right? Ax equals b. Okay, so it's an intersection of many, hyperplanes. Okay, which all of them are like convex sets. So this intersection is also going to be a convex set. So in the back, there is this theory which says that you will, there is no notion of local optima. Every optimum is a global optima here, right? And if you want to think of it in another way, like you just think of the feasible region. Let me just maybe include a new page here. See, what's happening is the feasible region is some polytope, right? Something of this form. The interior is what is the feasible region. Okay, and there is this vector that, even you had practice of doing this geometrically, right? So there is this some direction. So suppose this was the direction in which you go. So suppose this was the direction of minus c. So that's the direction in which you need to go to reach the optimum. Okay, so because that's the direction of decrease. Okay, so if you're starting somewhere here, now what's going to happen is perhaps if you go to this vertex, you're going to have an improvement. Okay, now again along this direction, if you go, there's going to be a component in the direction of minus c. Okay, so generally this is the direction in which you would go to get an improvement. So you keep on doing this till you reach the edge of the feasible region. You reach one end point. Okay, so once you reach here, at this point, only if you go in this way, the objective is going to improve. But now if you do that, you're going to just step out of the optimum, step out of the feasible region. So that's why at this point, if you intuitively, if you look at these, the reduced costs, right? For all these other variables, for all these other vertices, you're going to have, it's not going to improve your objective in any way. Okay, so that's why it is going to guaranteed at some point it will reach the true optimum. Okay, and it is a very it really makes use of this linearity in the objective, because the direction of improvement is the same for when you take any point. It's this gradient is going to be this in the same direction, right? So that is one thing it really makes use of in order to make an advance. Okay, so the direction which you should go, that is clearly defined. Okay, because of this minus c. Now you want to just ensure that you are at a vertex. So that's why you are doing this, all these operations. Rajneesh, I don't know if I answered your question. Does it make sense?
So ma'am, we will be just given some equations and we will be just told that you just find the optima where objective function is this one. So by just looking at those given equations, can we figure out that yeah, surely this will be a convex figure in that dimension? So we can use this one here, this all steps.
So this
just by looking at the equations.
Yeah, so if you have the linear program is a very specific form, right? This minimize C transpose X, Ax equals B, X greater than 0. So that is always going to be a convex region. Okay, there going to be no doubt about that. There's no way it can become a non-convex region, because it's, of course, each of these components are,
So suppose here, if instead of these five lines, if I'm given for this, the uppermost vertex is like that, it lies in between these two.
The uppermost vertex, this one, something here.
The uppermost vertex. So so if I'm given just 4 or 5 equations, then it is like this leftmost downward slope. Can you number the edges here?
Okay, so I'll just call it A, B, C, D, E.
So if I just hold this B and take it downwards.
This B, right? This one?
Yeah, and below the line joining AC, then it would be a concave region. And I would be given just 5 equations of these lines and I'll get that feasible region.
So something like this you're seeing?
Yes, ma'am. connect this with A and C.
Okay, so something like, okay, just one second. So something like this region you're going to say.
Yes, ma'am.
Okay. So can this happen in a linear program, right? So ideally this wouldn't occur in a linear program. So let's see why that doesn't happen. So you have this region and this one. Okay. Okay, this I just need to think of this one, like what is preventing this kind of regions from coming into this framework. Okay, so let me just take some time to think of this example and let you know. So the point is, this kind of a thing is not going to happen for linear programs. Okay, it's always going to be a convex region. Okay, but let me just think of this, and maybe let me just think of where it breaks the convexity thing, right? Why it doesn't come into the class of linear programs. Okay, yeah, that's a good question. So yeah, but is the rest of the idea clear, like how you would go about this procedure?
Yes, ma'am.
That's clear. Okay. So I just wanted to, so I will address this point in the next class, but I just also wanted to take a few more, some smaller points here, like about how you would choose the first BFS. So the way we did this is, we found an identity somewhere and we just used that as the basic feasible solution, and that was that was our starting point. And then we just followed this kind of a procedure, and the thing is that you at some point you will stop. Okay, so now how could you choose the first point? So if you have the inequality, the system given to you, if it is in this form, ax less than or equal to b, then what you would do is you will just add these slack variables. Okay, and this is going to give you a basis, this z vectors, whatever you add here, that will correspond to identity, and that's what you would use as a basic feasible solution. And this is the case that we did here. Okay, so now if you already have the system given to you as ax equals b, okay, this is a standard form. If you already had it in this form, now it's not necessary that you will have an identity somewhere in a. Okay, so then what is done many times is you just add some other variables here. So you add these ax plus y equals b. These are these new variables, and they're called these artificial variables. Okay, and you will have okay, so what you can do is you can use the simplex method to solve this system. Okay, this is a new system where you're trying to minimize the summation of y's, and y's are greater than or equal to 0. Okay, so now if this original system ax equals b is feasible, then the final solution you get here has to be y's are all 0. Okay, but the thing is that if you apply simplex on this, so here already you have a way to start the simplex method for this system, because this will have an identity, and at the end of it you're going to get some other basic feasible solution which is optimal here. Okay, and if the y's are all 0, then that will be a basic feasible solution for the original problem. Now use that as your use that basis to start off your the simplex method for your original system. Okay, so it's kind of a two-phase method where in the first step you solve another LP with artificial variables, find a BFS, and use this to solve the original LP. Okay, and so this is some ways in which you could start off. Okay, so in general, what the simplex algorithm in the matrix form, what you have is these two classes, right? The basic and non-basic variables you had. So you can have this kind of a partition. Okay, and at each step, in terms of the reduced cost, what you're doing is you're trying to find something of this form. For the non-basic variables, you're trying to find some quantity which does an improvement, which leads to an improvement. Okay, now you will see like in the next class, what I will do is, I'll introduce you to a concept called duality. So that kind of makes use of these cost coefficients. It has some connections to these kind of cost coefficients that we saw in the simplex method. And in general, duality is a very important concept. So general duality for constrained optimizations are, it's used in many places. And this LP duality will give you a start to understand duality in a more general sense. Okay, so I will stop here. Okay, and yeah, we will meet on Tuesday. Okay, so if there are any questions, I think I can stay for 5 minutes. There's another meeting. So yeah, I'll be here for some time. So thanks a lot for coming. Yeah, Rajneesh, regarding your question, there's one thing I think, this system would boil down to. So in the process of including Slack variables and all that, perhaps it boils down to, another system which makes it convex, like, some other system where, even these are connected, but the original objective will not change. So that could be one way to think of this. But anyway, I will just, just think of it more formally, and I will let you know. Okay.
Okay.